Okay. Okay.
So, well, it's getting close to 10 o'clock, and I would like to tell everyone a little bit about Doug. We all know him as an engineer who is provocative. He doesn't let things pass by without giving good commentary over the years. But I asked Doug to send me his a little brief bio, and he kindly did so. I didn't realize that he'd spent half of his career working for large Fortune 500 companies, Union Carbide, Quantum Chemical, and Equistar, for process engineering, supply chain planning, etc. And he's also then transitioned to spend the other half of his career selling, developing, and implementing supply chain management software for a startup computer software company, WAM Systems. So that's explains why he, when he comes to express an opinion, I can tell he's thinking of basics like supply chain management. He has a lot of experience there. He has a Bachelor of Science degree in chemical engineering from UW-Madison, a Master's of chemical engineering from University of California, Berkeley, and an MBA in finance from New York University. So that's a excellent background for his topic today, which is going to be on the new concrete. I think Bill Gates would enjoy being present today because he's been pushing this for a while, and we don't know many details. So Doug, we're delighted that you got into this, and you have the floor.
Oh, great. So I'm going to share my slides.
Good.
And I have to first tell everybody that, as I mentioned to Richard earlier, he sort of roped me into this earlier in the year. And I really don't know. I know about as much about concrete as everybody else, but I didn't know as much as I know now. And having gotten into it, I learned some things that culminated in my sitting in on a seminar at the Energy Institute that I'll get into later in this talk, that I think is a real opportunity to do something about the climate issue. So as I go through this, I just want to let everybody know, Richard told you I'm an engineer by training, and so I really am interested in how everything works, and so I'm going to make you all go through what I like doing, which is learning how things work, for better or for worse. So let's go. Okay, so let me see if I can get this thing to. So just to start off, what is concrete? It's we see it everywhere. It's a heavy, rough building material made from a mixture of broken stone or gravel. That's the aggregate that's thrown into it, and then sand, cement, and water. And it can be spread or poured into molds that forms a mass resembling stone on hardening. It's used everywhere because it's really so convenient. You can shape it into just about anything if you put it into a mold, and so it's relatively inexpensive and very very useful in building so many different things.
Could I ask a question at this point?
Sure.
Doug, does the process of the solidification of concrete, does that take up CO2 from the air?
It can, but we'll get into a little bit of that, actually.
Okay, good.
So in not completely in contrast, but compared to concrete, cement is the binder. It's the chemical substance that's used for construction that sets, hardens, and adheres to other materials to bind them together. It is sort of a glue. And I know for myself, I think I always in the past used them synonymously, and they're really not. The aggregate that goes into concrete can be, pea gravel, or it could be stones or broken up material. So let's differentiate between cement and concrete, and I think you'll see why here in a little bit. So this is hold on a second. So this is the chemistry behind cement and concrete, and this is really kind of this is in part what Richard's getting to, that to make cement, and in particular Portland cement, you take limestone, which is calcium carbonate, CaCO3, and you heat it up in a kiln. It drives off the CO2, the carbon dioxide, and leaves you with lime, which is just simply calcium oxide. And then you combine that lime with silicon dioxide, which is sand, and you get actually several different varieties of this calcium silicate, or this calcium oxide silicate compound. And it turns out that that actually the three-member version of that reflect or develops most of the strength in cement and concrete itself. You also add, or there's also alumina, that third one down, this one right here. This alumina that you add comes in the form of we'll get into that in a second. But there are a number of different components in particular in Portland cement, and each one affects the properties of the cement, its strength, its ability to avoid cracking, its heat resistance, all sorts of properties that are affected by these various components that end up in Portland cement. If you add a bunch of this alumina and iron oxide, then you end up with hydraulic cement. Hydraulic cement is the version of this that actually it will harden underwater, because cement, as it's forming, you don't evaporate water; it incorporates water in its crystalline structure. Another thing that I would assume that everybody's heard about is this slaked lime. I never really knew what it was before, but it's just calcium hydroxide. It's calcium, or the lime, and you add water to it, and it's often used as a cheap mortar. And then you also see here that if you add CO2 to the calcium hydroxide, that slaked lime, it will actually absorb CO2, which is the reaction that Richard was just alluding to. So during the hardening, or when you add water to Portland cement, after a time, it will actually absorb some CO2 from the air.
Quick question, if I could, Doug. does Portland cement include mixtures of the top three in your previous slide? Or,
Yeah,
or does it
actually,
also include
so-
slate lime?
Yeah, so I'm going to get into that right here. That's
Okay. Okay.
a great
Good.
question.
Okay. Yeah.
So it turns out, and you can see it here, this is Portland cement composition. And you see in the mass concentrations that they vary quite a bit. So as to how much of each of these components end up comprising the ultimate cement that you use. And I'll get into this even in more detail a little bit later, but the fact that you see this variation is a result really over a long period of time in the development of cement itself and how to concoct different recipes that end up with different properties. So the cement, for example, that's used for example, in a nuclear reactor shell would be different than the cement that you would use to pour a sidewalk. The requirements, the test, probably the testing as well, of the two are quite different. And yet again, different is something that you would line a chimney with. For example, to line a chimney, you put a lot of alumina in there. It's very, you end up with a cement, a Portland cement that is very resistant to temperature, but it's prone to sulfur attack, for example. So there are these trade-offs in cement that it's sort of like any other product you can imagine, that you produce this material, and depending on what your end use is, you use a slightly different formula. So you can see here that this tricalcium silicate, it hydrates to create strength and volume stability in the cement. The dicalcium silicate, which is formed before the tri version, it slowly hardens. So you can imagine that if let's say you're mixing up a batch of concrete at the concrete plant, you've got to transport it 50 miles to your job site, you don't want the concrete hardening inside the concrete truck. So you actually have to mix this stuff in such a way that it doesn't harden that quickly. And one of the ways of doing that is you add this aluminate, this tricalcium aluminate, and that's very reactive, and it actually forms a precursor to the ultimate dicalcium silicate that forms the strongest, I guess creates the strength, or results in the strength in the ultimate concrete. So you can see here these different elements or these different compounds that you add. The last one in the list I thought was pretty interesting. This gypsum that you add. Again, it's used to slow down the curing of the concrete or of the cement, and it does that by reacting relatively quickly initially. It results in high initial strength of the cement, so it keeps it from flowing and that sort of thing, but it slows down the formation of this dicalcium silicate, and so allows the cement and the concrete to flow better when you're forming it in molds or in forms. And obviously that's an important consideration, depending again on what you're using or what you're building. So again, here's a typical concentration profile of Portland cement. And I'm gonna go through this a little bit of detail because I personally found it interesting. So this is the process this is the chemistry that occurs when you add water to cement. So this tricalcium aluminate first reacts with the gypsum. Remember, the gypsum has sulfate in it. And it, I think everybody knows that gypsum is what you make wallboard out of, or sheetrock. It's in sheetrock. And this water, it produces this compound that's called ettringite, and it actually also releases quite a bit of heat. And it's this formation of ettringite that slows down the ultimate reactions that result in the hardening of the cement and the reaction with the aggregate that's in the concrete. And the ettringite, it consists of long crystals that are really only stable in a solution with gypsum. So it turns out that it's not stable without the gypsum, and it ultimately doesn't contribute to any of the strength in the cement glue. But it's important to slow things down initially. Then the tricalcium silicate is hydrated, and it produces this calcium silicate hydrates. Okay, so it combines then with the calcium or the lime that's in the cement, and again produces more heat. So you may, I know from my own experience, if you're say using cement out of a bag or something like that, and you get it on you, it will actually create both a chemical burn and actually a sensible burn to your skin. Okay, so this tricalcium silicate, it has a short networked fiber structure, and that contributes greatly to the initial strength of the cement glue. So once all the gypsum is used up, the ettringite that was formed becomes unstable, and it reacts with any remaining tricalcium aluminate to form this monosulfate. And what this does is, because this is unstable, it actually can create voids in the cement and in the concrete. And those voids then allow water to come in and a different crystal structure to appear and to grow. And these bigger crystals then can result in cracking of the concrete. And I know it's sort of interesting. I'm not a civil engineer by training, but one of my brothers was a civil engineer, and I remember him telling me once that all concrete cracks eventually. And so if you've ever had a concrete driveway or concrete in your garage or something like that, or on their basement floor, you're always disappointed when you start seeing cracks. You think that, oh, they didn't pour it right, they didn't do something right with it. But this exposure to water and ultimately this change in crystal structure can result in these cracks. And that obviously then weakens the concrete. And it actually, and we'll get into this a little bit, it'll expose any structural steel in particular that's embedded in that concrete to the elements, which can result in corrosion and weakening of a structure, for example. So, clearly when you're using this to build, say, tall buildings or something like that, you have to be sensitive to that.
Especially if you're in Turkey.
Especially, really anywhere in the world,
Yes.
including here in the US, right?
Sure.
So this dicalcium silicate, it also hydrates to form a calcium silicate hydrate and more heat. And it contributes to the strength of the cement paste. And it's interesting, I copied this out of documents online, and cement is always called a paste. I've never thought about it in those terms before, but that's one of the things that I learned as a result of this this dive into concrete. This reaction proceeds at a slower rate, and so it develops its strength more slowly, and but the compound itself is responsible for long-term strength of the Portland cement concrete, and it does that by slowly curing over time.
Could I ask a question?
Sure.
The concrete, as I understand it, is very strong under compressive stress and very weak under tensile stress, which
Correct.
is why you have the, and the question is that also involved in the choice of cement?
I think, Don, that certain cements, I'll say that no cement is terribly strong in tensile stress, and I think that to gain that additional strength, that's what you add the structural steel to it for, and it's also important that it be able to undergo some torsion, right? Either twisting or bending, and certainly buildings, that have concrete in them certainly do sway back and forth to some extent, and so there are a lot of other compounds that are added to cement, including polymers, to improve the ability of the concrete to flex more, in spite of the fact that it doesn't like doing that. Again, I'm not an expert in all this. I know a lot more than I used to know, I have to tell you, but I know I've read a little bit about that as well, and you're right. Generally speaking, concrete is used to support things as opposed to hang things, let's say. So you see here, this slide actually gets into some more of these reactions that take place that result in these crystals becoming larger and creating a problem potentially in some concrete. So if it's not mixed properly, if you don't have the right formula, you can end up with problems in the concrete. And I know I've seen some of this, or certainly I recognize some of this in foundation walls. Sometimes you'll see some it appears to be crazing pattern in foundation walls, and I think that's because the mixture, possibly it wasn't completely mixed, possibly it wasn't The components weren't in the right proportion. I can't tell you exactly, but I know I've read about it now, and I've actually seen it in real life. Having said all this about the sort of the underlying chemistry, this is really why concrete is desirable as a construction material. So concrete has a lot of properties that make it popular. And it's this correct proportion of ingredients, placement, and curing that are needed for the properties to be optimal. Good quality concrete has many advantages. First, it's economical when the ingredients are readily available. Concrete's long life and relatively low maintenance requirements increase its economic benefits. Concrete's not as likely to rot, corrode, or decay as other building materials. It can do all of those things, but it's just better than some other building materials. It has the ability to be molded or cast into almost any desired shape. I think that's something that after reading it, I have real appreciation for. And the building of the molds and casting can occur on the work site, which reduces costs. Obviously, you don't have to transport these things. Although we've seen certainly that in some cases, these precast concrete shapes are brought to the site. So there's obviously a trade-off there at times. It's not combustible, makes it fire safe, and it's able to withstand high temperatures. In particular, with certain formulations. I mentioned to you that if you have a lot of alumina in the concrete, I believe its melting point then is somewhere up in the 1800 degrees C range. It's resistant to wind, water, rodents, and insects. And so it's often used for storm shelters. And it does have some limitations. And this goes to Don's point. It has relatively low tensile strength, which means you can't generally pull it apart. You don't want it in that form of stress. It has relatively low ductility and low strength to weight ratio. So it takes a lot of weight to make it stronger. And it's susceptible to cracking. In spite of that, it remains the material of choice for many applications, regardless of these limitations. So what's the impact? Well, but before I go on to this, I just want to point out that one of the things that I learned about concrete is that as long as it's been around and as much as it's been studied, it really isn't as well understood as you would expect. And it turns out that concrete, the specification for concrete is not so much based on its ultimate properties, but it's based on a formulation. So, for example, it's my understanding that if you were to actually require or specify concrete for example, a nuclear power plant shell, the specification for it is in terms of the components, the recipe for the concrete, and not necessarily a physical test that determines that the recipe resulted in the proper physical properties. And that's because it's so complicated. There are so many Well, the crystal structure is varied. There are so many components in it that over time, the industry has learned how to make concrete, and it's specified based on these recipes. And actually that creates some problems in replacing it, and we'll get into that here. So concrete's produced using this cement mixed with an aggregate, and the aggregates, which is a grainy blend of materials. It can be stone or sand, it can be all kinds of things. And after mixing, the concrete's poured into the mold. Everybody's seen this, I suspect, and left to harden, then used in building. The aggregates are sourced usually from a local body of water and crushed. And that process of producing the aggregate releases really almost no carbon emissions. Sure, there's probably some energy used in doing that, but for the most part, the cement itself is the true problem when it comes to carbon footprint. And the cement process, the process of producing this Portland cement, is for the most part the sole reason why the concrete industry makes up about 8% of overall global emissions of CO2. So this is a distribution of those emissions, and you can see here the concrete sits in this little piece of pie right here. So this talk is supposed to be about alternatives to cement, but I needed to learn about cement to begin with. And so I dragged you through that too. After all, I had to be dragged through it. It's only fair.
Sure.
So there are alternative binders to Portland cement, and some of them are listed here. We're going to go through them in more detail here in a minute. One of the things that is added to cement often is fly ash. And we're going to talk about fly ash quite a bit here. But fly ash is something, when you're burning coal, other than the carbon that's in the coal, there's a lot of other mineral material in that coal, and it ends up coming out the top of the stack or being precipitated out as fly ash. And there is an enormous amount of fly ash that makes up lagoons and just fields of it around the U.S. and really around the world. Every coal-fired power plant in the world produces fly ash, and it's got to go somewhere. And so it's, generally speaking, been piled up and spread out and fills in various parts of the land around the U.S. as well as the rest of the world. So there's an enormous amount of it available. I know that for example, Duke Power down in I think I would say it's mostly the southeast part of the U.S. has had problems with this, and there's an issue with ameliorating large collections of it, large piles of it, and the Tennessee Valley Authority likewise has collected an enormous amount of this over the years. So in addition to that, there are, as I mentioned earlier, there are polymers that are added to cement. And I don't know if anybody's done this, but if you ever say grout your bathroom, something like that, or make cement or make mortar for some project you're doing around the house, oftentimes you can add these polymers to the cement that you're using, to make them more resilient. Those are additional components in this cement that to some extent replace the Portland cement that we use in larger amounts. It turns out that cement's been used forever. And so I found this online that the Babylonians and Assyrians used asphalt to bind together burnt brick or alabaster slabs. And then in ancient Egypt, stone blocks were cemented together with a mortar made of sand and roughly burnt gypsum, which often contained calcium carbonate. And therefore, this would have contained lime. And this is actually a type of mortar that we sometimes use even today, to build a brick wall or a stone wall in particular, just to fill in the gaps between stones. So sulfo-aluminate cements, you burn limestone, calcium carbonate, bauxite, and which is what contains the aluminum, and gypsum at roughly 1300 degrees centigrade, and you get this 20 to 70% of tetracalcium trialuminate sulfate, and you use less limestone when you do this, and because of that, you produce a little bit less carbon dioxide. You use more gypsum, which is that calcium sulfate, and you end up with something that is a little bit more porous. And when you produce this stuff in a kiln, you can imagine you're melting everything, and then it's sort of solidifying as you cool it. And then to use it in producing concrete, it's necessary then to grind it. And so this material, I guess before it's ground, it's generally referred to as clinker. And so that clinker is then ground to a finer powder, and that's what typically we would buy in a bag, say at Menards or at Home Depot or a hardware store.
What does CSA stand for again?
CSA is you'll see these I think it's up here. Let's see, it would be a calcium sulfate aluminate, something like that.
Thank you. Good.
One of the things that I know I had to get used to when I was reading articles on this was that the C it normally refers to calcium as opposed to carbon, and because these are all hydrated crystal structures, you can imagine that the chemical formulas are really long, because there's a lot of water that goes into this crystal structure. And so what they do is to shorten everything to single letters, and so you have to get used to the abbreviations.
Thank you.
So it turns out that to produce these cements, generally speaking, you have to put into solution one way or another the silica. And so I mentioned earlier that you'll oftentimes, in fact, many times it's specified that you have a minimum amount of fly ash in the cement that you're producing, the Portland cement that you're producing. That fly ash has a lot of silica in it, and it's important that the fly ash that's used in producing Portland cement in these processes, in the processes that are normally used commercially today, that fly ash be amorphous as opposed to crystalline. And that's because the crystalline version is very difficult to put into solution and then get to react with the other components of the cement. So, you'll see reference in here of amorphous or vitreous, vitreous being glass-like calcium aluminosilicate precursors. These are, and the alkali is the basic material, is used to solvate, to put into solution these minerals that make up the cement and get them to interact with one another. Okay, and these are all considered to be geopolymers in the sense that you're using these materials really that come from the ground, and they're sodium and potassium salts or oxides, alumina, silica, and water. And then in addition to that, in addition to fly ash, iron ore slag or iron slag from production of steel can be used. And likewise, silica fines can be used in this system. So all of these can be subject to sulfur attack. And the sulfur attack occurs when you remember that we have that gypsum in there that has sulfate in it. And if you have sulfur, or you get sulfur into the voids in the concrete or in the cement, then the crystal structure changes and those crystals get bigger, and then that causes the cracking. So again, this is something in this formulation that tries to avoid the voids from forming and prevent this conversion of these crystals to larger crystal structure. The geopolymers are attractive because the natural and industrial silico-aluminate waste can be used as precursors. That's fly ash. That's slag from iron or from steel manufacturing. And the sediments in the reservoirs also contain a lot of alumina and silica, obviously. So these sediments that are forming upstream of dams that are along rivers in certainly in the U.S., but really around the world. You can imagine that this big dam in China is going to that the reservoir formed by that dam is going to slowly but surely fill up with sediment, and it'll have to be dredged out. These materials are available from those sources. And so again, this issue with these voids being created in the cement, that it's a concern because you get voids in the cement. It allows they allow water to infiltrate concrete, and then that attacks the structural steel that is oftentimes included in the concrete itself. And just to give you a sense as to, I mean, I will say that this sort of hammered home the point of cement or Portland cement being complicated. This is just a ternary diagram. So over here on the lower left is calcium oxide or lime. Here's the alumina over here, 100% alumina. And then up here is 100% sand. And so cement is generally speaking, some mixture of this. And these are all of the different properties that can occur as you vary this concentration of these three components in typical Portland cement. And I can't imagine trying to concoct some function, some mathematical function that you could generally use to predict properties, based on what I'm looking at right now.
Could I ask a quick question here? This is a fascinating diagram, Doug. I was delighted to see something this interesting. So the impression I get from you is that Portland cement could be anywhere in this triangle. And so my question is sort of twofold. Where does the typical Portland cement that you see going down the road to the average building foundation lie in this triangle? And if I understand you correctly, the more you go to the CaO lower left corner, the more CO2 gets released in the production of the stuff, right?
Yeah, I think that would generally be true. Your last statement. To be honest with you, I don't know where. It would be. It's an interesting question. I don't know the answer to it. But if I went to, as I said, Menards to buy a bag of Portland cement, I don't know what I would get on this diagram. Yeah. It would be actually the way to perhaps if it's possible, I guess that the formulation is on the bag, but I suspect it isn't. And it would probably refer. I don't know how it would be specified on the bag itself, to be honest with you.
I get the impression that the word Portland has historically been associated with reasonably good quality concrete or cement, and yet the diagram that you portray shows huge variability in various qualities. So it rather than reassure us after looking at the diagram, I'm rather concerned that there are a lot of unknowns to the buyer.
Well, it isn't, actually, I want to reemphasize that there's an enormous amount of experience, practical experience using cement and concrete, right? We've used it for years and years and years, and it's been around since, I mentioned it's been around for literally thousands of years. And so this accumulated experience has led people to specify formulae for different qualities or different types of cement. And Portland, I believe originally referred to I think of a town in Great Britain where this stuff was made. I believe that's true. That's what I seem to remember. But having said that, the confidence that we have in concrete in general, in cement in general, is because of this experience that we have using it. And the fact that we can specify, if we specify a certain percentage of these different components, that we will get something that has minimal properties that will be satisfactory for the application.
Yeah. Tony, you had a question?
Yeah, Doug, I'm just wondering, looking at this chart, the oval that's kind of shaded in the
maybe that's
center,
the sweet.
Yes, yeah. Is that the sweet spot?
To be honest with you, I don't know. I didn't go into it enough, and well, you've got me going now. I will find out. I will find out, actually.
I know the feeling, Doug, definitely.
I warned you to start with that. I started off knowing relatively little about this. I know a lot more than I used to, but I'm still not.
Well, this is great. This is just what we're here for, is to learn from each other. And thank you, Doug, for getting us all riled up.
Yeah. So, what are some of the alternatives to this? I mean, that's really what this talk was supposed to be about.
Yep.
And I'm going to go through a list of them here. And the first one that was, I found a whole bunch of these things. So bamboo, as you see here in this picture, can be used as as an alternative to putting in structural steel, for example. Bamboo, obviously, being pretty flexible. It's local. It's available locally in some parts of the world. And it's apparently becoming quite popular to reinforce concrete. Doesn't affect the cement at all, however. Okay, it has impressive tensile strength, and it's lightweight, which is actually lightweighting things can be valuable because it means that you need less strength down below to support what's above it. Okay, so you can imagine you're building a tall building, you're putting quite a bit of concrete up high in the air, and you want that to be as light as possible, if possible. And so using bamboo obviously could accomplish that. And bamboo, anybody who's ever had any of it growing in their yard knows it grows fast. And it spreads fast too. Obviously, steel is used, so it's one of its advantages is that when you break up old concrete, you can reuse that steel. Wood. So actually, as a complete replacement to concrete in particular, we can use wood, and one of the interesting, or a couple of the interesting aspects of it are that when we're growing trees, we are sequestering carbon, but likewise, if you take a tree and you put it into a building like this, you've sequestered that carbon for a long time. So there's been a lot of discussion about the replacement in buildings. In particular, building with wood structure, as opposed to, for example, sometimes, in particular, if you look at buildings today, they're using these aluminum, I think generally aluminum 2x4s in the walls, and actually using wood is a better idea from the perspective of sequestering carbon, because you put it in there and it's going to be there for 100 years or more. And likewise, it's also, generally speaking, as a high strength to weight ratio. This was interesting to me, the use of straw bales to build. And it says, when houses were made only from natural and locally available materials, straw bale buildings were quite popular. They're used for walls inside a frame and replace materials like concrete, wood, and gypsum. They would provide a lot of insulation from any kind of climate, affordable and sustainable, because they're renewable. And apparently, I haven't seen any of these in Madison, but lots of tiny houses and eco-friendly homes are being made using straw bales. Many are going off-grid and building hobbit homes. It's kind of an interesting concept. And then using it with concrete is a matter of stirring it in. So clearly you could. Sorry, say that again. Was that a mistake? So, clearly you could mix cement in with the straw and use it as a sort of a structural enhancement as well.
Isn't this a upgrade of Adobe construction?
I think you're right. I think you're right, Don. I think it would be similar to that, because certainly I think Adobe does mix grass in with the mud, right?
Yes, I think that's right.
Yeah. So here's another alternative, possibly similar to Adobe, been around for thousands of years, using rammed earth, typically using bamboo or rebar to make them safer. Also reduces the amount of labor needed to make strong walls. It can be an alternative to a concrete driveway, because you can add in pebbles or larger stones, and it holds up like Roman roads still do today. It's not an alternative to a concrete garage floor, though, where a flat floor is needed for working on do-it-yourself projects. And then glasscrete. So I don't know if any of you have seen any of these, but I know in our neighborhood here, I've seen a driveway that's actually been created like this, where these blocks are arranged in a pattern like this, and then grass actually grows in between in the what would typically be a mortar. In this case, it's probably more like some type of dirt that packs in between, and then the grass grows in between and sort of cements everything in place. And it's sort of pleasing to the eye, and it helps to drain the surface, which has a very significant benefit really around our Four Lakes area, because we don't have as much water then draining into the lakes, and helps to drain your property as well. And clearly this would reduce the overall amount of cement that you would use. So here's another material that can be used: hempcrete, just another substitute for perhaps a hay bale, with in this case it can be bound with lime. I'm sure that you could mix cement with it as well. And it can be a locally available material, so lower your costs and lower the weight. I'm sure that you get higher strength to weight ratio in this case. So here's ashcrete. So this is you use fly ash in making the cement, and I think that you can use a variable amount of fly ash when you're producing cement. I think that based on something that someone said to me, I haven't verified this independently, but my understanding is that Portland cement in the state of Wisconsin requires a minimum amount of fly ash, and that's because of its composition includes a fair amount of particular type of silica, and it's only certain fly ash that can be used in making this Portland cement. I mentioned that fly ash in general, to be used in the process that produces Portland cement, needs to be amorphous. And fly ash that's been exposed to a lot of water and has then been allowed to settle over long periods of time, can crystallize, and that or the silicate in that fly ash can crystallize, and that makes it unusable in that process. Then using sawdust, obviously mixing, another alternative is using sawdust in the mix instead of bamboo or straw bales or whatever else. Waste paper, another alternative. You can cut up or mix up all this paper and then mix it in with the cement. So here's this is a material that can be grown into bricks. So the root structure of fungi or mushrooms, and then it's grown in molds, and it actually forms around other natural materials like straw, and you can form bricks from it, and then air dry them and use them as bricks and cement them together, right?
That's cool.
So very lightweight, renewable, would other than the mortar that you would use, would completely eliminate the production of CO2. In fact, it would the formation of the brick itself would undoubtedly consume CO2. Then what's called ferrock, which is where you're recycling materials like steel dust, and you're mixing that in with this cement, with this Portland cement. You're making it part of this Portland cement, and this process absorbs carbon dioxide during drying and hardening. You know, this is something that I think Richard, you were wondering about earlier. So
Yeah.
it actually absorbs more CO2 than it creates, because it's forming a carbonate as it's hardening.
It's great.
And it says here that about 95% of ferrock is made from recycled materials such as waste steel dust coming out of steel mills and silica from ground up glass. So apparently there is a fair amount of this silica dust that I don't know if it comes from the recycling of glass or it comes from glass manufacturing facilities, but it apparently is available. I know I'm going to bring this up here in a little bit. Again, somebody has mentioned this to me. And
Doug, do you know if Bill Gates favored one over the other? I can recall in reading his book and reviewing it, he talked about other substitutes, but he wasn't very specific. Do you happen to know if he favored any of these?
I don't. I didn't read anything that he's written. I haven't been.
Okay, I will look into it. Maybe.
Well, I'm going to get into. What I personally favor here in a bit. But and I may very well make him aware of it.
Yes, excellent. Yeah, we can both dig into this and put together something for this group maybe in a week or so. If Alan Pentikoff can give us a couple of minutes next week from his solar talk, just if he can give us 5 minutes or so to review some of these questions, it would be nice to know what he thinks.
Yeah. So anyway, this particular alternative is quite a bit stronger because it has this steel or this steel dust, and it ends up being much stronger than typical Portland cement. But apparently, it can also be expensive.
Yeah, Bill said that.
So and expense is a big issue, and I'm going to get into that here in just a bit. So blast furnace slag can also be used. So, you get the slag out of a blast furnace, and you then grind it up and use it instead of cement, or as part of the cement. Okay, so it ends up improving the durability of the concrete, and it does that again, I suspect, by eliminating some of these voids and pores that end up in cement and in concrete. Microsilica, I mentioned this earlier, that you end up with very fine silica, which likewise can be used in producing cement. Concrete debris, we're seeing more and more of this right nowadays. We're seeing old, we actually just saw a building come down on campus, and we no longer just destroy buildings and haul them off to the dump. We now deconstruct buildings and recover as many materials as we can from them, for the most part, because I think in part it's to be honest with you, I don't know what the actual economics of the alternative of this is, of deconstructing versus putting material into a landfill. I don't know what the economic trade-off is right now. Ultimately, we would have to do this because there won't be any room for landfills anymore.
Yeah.
So, but in any case, nowadays, I certainly see a lot of this happening. When concrete is busted up, I suspect that it does end up back in new pavement or buildings or whatever, depending again on the properties that are required of the concrete that goes into a project. And you see here that in here, it's used as a concrete aggregate, doesn't substitute for cement. Okay, so this substitutes as the aggregate. Capillary action and permeability of concrete containing recycled concrete is increased. And so that results in faster degradation of that product that's being used. And then it says at the bottom, many of these effects can be offset by using additives. So you're adding perhaps polymers and that sort of thing to fill in those voids. Post-consumer glass, ground up glass. We talked about that a little bit ago, that certainly the fines from a process like this that grinds up glass. And I know that when I drive down the road, sometimes I think I see ground up glass in asphalt. So I think that this ground up glass can be used all over the place. Plastic waste. So plastic waste can actually be mixed into concrete. It actually can create spaces so as to sort of lightweight the resulting concrete structure without losing strength, because most of the strength from any I guess mechanical form comes from the outer shell as opposed to what's on the interior. And because of that, you can create this large void in the middle of the structure that can't be penetrated and won't change shape, therefore won't result in cracking, and you'll end up with the same strength but a much lighter, actually presumably less expensive alternative to using a whole bunch of concrete. And I'll give you another example of that here in just a second. So here are these this wall system, and these walls, I think that these walls are actually, they can be made off-site and transported into the construction site and erected and assembled. And they are really a composite of a bunch of different things. So you see here on the right that there's steel in this form, and there's other I guess adjuncts included in this form that would improve insulation and strength simultaneously, and also turns out in noise proofing. So I can imagine some of these buildings that are put up alongside highways would benefit from something like this. And then here's a material that's made with desert sand, which is usually too fine-grained to be used, and it's used to create a brick. Ends up being as strong as concrete and doesn't have the carbon footprint of concrete. This is I found out about this from a neighbor of mine. You may or may not know that when the Laban Center, which is where the women's hockey team, the national champion women's hockey team plays hockey on campus, was produced or was built using this bubble deck process. And if you notice in this picture, you see these bubbles here, these really, I think they're plastic balls, and they are spaced within a steel frame, and they occupy volume in when you're producing when you're forming a concrete deck or a floor in a building. And you're using a lot less concrete, and you're lightweighting that floor. So again, you don't have to have as much structural steel and structural material holding that floor up from below, because it's much lighter. And this process was used by Findorf, actually, when they built the Laban Center. It was I think that this process was developed in Europe, and Findorf became qualified to use it here in the U.S., and they experimented with it when they built the Laban Center. And this is a picture that I got online, and a friend, as I said, one of my neighbors, a friend of mine, mentioned this to me, and so I actually talked to him about it a little bit. And per him, from what he told me, was that this is the only system that's actually been tested and used in real life. A lot of other ideas have been forwarded to replace concrete and to lightweight concrete, but this is one that in fact has been used, experimented with, and has been successful.
That's fascinating, Bubble Deck. Thank you so much. I'm going to have to drop out. I'll let you close the meeting, but I'm looking forward to the recording, because this is a wonderful talk. And thank you again, Doug. We'll look forward to hearing from.
Well, here's the one that you wanted. This is the one that you actually asked me about, which is the bacterial concrete. So you can drop out right after this, or right, do it if you want.
Okay.
So this is a material that actually it combines sand, hydrogel, which probably has a growth, some growth material in it, and a bacteria, boy, I don't know if I can pronounce that properly. So I'm not going to.
Synechococcus.
Synechococcus, okay. Which is a photosynthetic cyanobacterium, and it converts CO2 to sugars during photosynthesis. And so what you do is you put a little bit of this in one of these molds, and you inoculate it with the bacterium in this sand hydrogel scaffold. So you mix the sand in with the hydrogel, and the bacteria do everything else. And essentially they form these bricks. And you can take a parent brick using temperature and humidity, and you can form another brick. So they sort of propagate on their own.
That's cool.
And so there turns out that there's a trade-off that exists between the biological viability and mechanical performance, because the gelatin gains its maximal strength when it's dehydrated, but the bacteria require humidity to function. So there's a kind of a sweet middle ground where this works best, or where these things grow best. And what also is interesting about this is I mentioned several times that the concrete in general develops cracks, and I know that this is I'm pretty sure this is being done now, where some of this is being mixed in with concrete, and it will heal small cracks in concrete so as to prevent them from leaking, or allowing water to enter the concrete, enter the cement, get at steel and corrode the the steel that provides a lot of strength to the concrete.
Thank you.
Okay, so what I'm going to get into now is really was what I would describe as a serendipitous revelation to me. In addition to a lot of other things that I do, and attending this class is one of them, I attend a seminar series at the Energy Institute, and many of you may do that as well from time to time. I try to catch all of them. And probably a month and a half ago, it just turned out I was obligated to do this talk, and turned out that there was going to be a talk given on an alternative to cement that would capture and sequester carbon dioxide. And naturally I was very interested in this, so I attended the lecture. And this process that's being developed here at the University of Wisconsin by a guy from I think he's from biological engineering group. I know that he has an office at the Energy Institute. Another guy who is a civil engineer, and I know that they are also working with somebody from political policy making, as well as another colleague from Penn State who is a concrete expert. So it's a collaboration among a number of different disciplines. And there is the professor in civil engineering has patented a process that produces an alternative to Portland cement that generates no carbon dioxide, and in fact absorbs CO2 in producing it. And it is I mentioned this earlier, you may remember the term alkali activated material. So the alkali, again, is used to solubilize the adjuncts. So you're adding a bunch of things together, getting them to interact with one another and to precipitate out a product that can be used as an alternative to Portland cement. And these adjuncts that are added include fly ash, which we've talked about quite a bit, silica fines, and iron slag. And I mentioned that there's a lot of fly ash out there. And another interesting aspect of this particular process that I think I've mentioned, that the fly ash that must be used in Portland cement has to be amorphous. The fly ash that can be used in this process doesn't require that that it be amorphous. It can be crystalline or amorphous. And because of that, it makes available to it an enormous amount of additional fly ash that would typically have to be dealt with to stabilize it, to prevent it from flowing under, big rainstorms and that sort of thing. And so it's very possible, from what I understand, that fly ash might be available for next to zero cost, or perhaps even someone might even pay to have it removed and reused. So that affects the economics of this process significantly, you can imagine. And I'm gonna get into that here in just a second. But I wanted to point out that this is a process that's under development right now. And this is what the process looks like. I won't go into an enormous amount of detail, but what you should see here is that that actually this is the patented process. This is, if you look this process up in the patent literature, you'll find this process flow. And you'll see that it actually specifies in the diagram a CO2-rich flue gas, as if this is carbon dioxide coming from, say, a power plant or something like that, or a steam boiler or something. Well, it turns out that they actually prefer not to get the CO2 from that. They'd actually prefer to get it from ambient air. And that actually allows them to make these plants much smaller. So much like in the nuclear industry, smaller plants have some advantage, because once you produce cement, concrete, you have to transport it to the job site. You don't want to have to transport it halfway across the country. So actually having smaller plants closer to where the product is going to be used is an advantage. And being able to capture CO2 from ambient air is also an advantage. You can place these plants in lots of different places. And it has some economic, actually business-oriented advantages, because the plants can be smaller. You don't have a huge capital outlay initially. So you can imagine that just like with a nuclear plant, nuclear plants, when you make them really large, they get to be so expensive that people can't finance their construction. They have to get governmental organizations or some really deep pocket involved in order to finance the development of a plant that size. These plants can be much, much smaller, and that actually lends their use not only to different geographical locations in the U.S., but concrete is used around the world. We know that Turkey, for example, Turkey and Syria they're going to consume a lot of concrete in the next few years, rebuilding the entire country. So this kind of alternative could have a very significant impact on both CO2 emissions from the production of Portland cement, where this process would produce no CO2, would result in no CO2 emissions. Not only that, but it actually absorbs about roughly for every pound of, or for every 6 pounds of alternative cement that are produced by this process, you absorb about a pound of CO2. So I'm going to show you the numbers here, on how that works out from a climate perspective. In any case, you'll see that they're bringing CO2 into here. They absorb it. They absorb the CO2 in a solution of I think they're using potassium hydroxide here. I can't remember, but the potassium hydroxide absorbs the CO2, makes a potassium carbonate, and they then feed that. They feed that into this carbonation reactor. Okay, so they're absorbing the CO2 here. They're feeding it into here. They form the carbonate. They filter it out. They put that basic solution down into here, and here's where they're bringing in their adjuncts and mixing all of that together in here, precipitating that out, and then filtering out the silicon rich residue, which is the cement that they're producing. And then they degas the CO2, they compress it, they put it back in here, or essentially they recycle all of the CO2 in the process. So any CO2 that they've captured up here, they keep in the process recycling it, and they then also will recycle this this hydroxide that they're using to solubilize all of these components. So the point of this is that this process both absorbs CO2 from the atmosphere, a large amount of CO2 from the atmosphere, and at the same time replaces a product that produces CO2, produces an enormous amount of CO2 with something that doesn't produce any CO2. So you can imagine, again, I mentioned earlier that right now, Portland cement manufacturing in the world accounts for something in the neighborhood of 8% of all CO2 emissions. And so by replacing that product with this alternative, you would be eliminating a stream of 8% of the current emissions in the world. And 8% is about 3 gigatons of CO2 a year. I think based on number that I looked up this morning, the total emissions of CO2 annually are somewhere in the neighborhood of 37 gigatons per year, and 8% of that is roughly 3. Okay, so you would be essentially removing that from the input stream, and then in addition to that, getting rid or absorbing, I think it's another. Well, actually, I have the numbers here. Let's see. So here's what the potential impact of this process might be. So first of all, no CO2 produced. Portland cement produces around 0.9 pounds of CO2 per pound of cement. And the annual worldwide production of Portland cement is about 4.1 billion metric tons or gigatons per year. Therefore, you could potentially decrease annual CO2 emissions by about 3.6 billion metric tons of CO2 per year. Then the CO2 consumed and embedded or sequestered in the cement, it's about 15% of the final product. And if you assume product substitution 1-to-1, therefore the CO2 captured and sequestered annually would be about 0.6 billion metric tons annually. So the total would be around 4.2 billion metric tons annually. Okay. I'm going to.
Dave, this is extraordinarily and exciting. And what's the time scale for this effect?
It's interesting. In the discussions that I've had with one of the people who is developing this, there are lots of business aspects of this. So let me see if I have more information here. Hold on. Okay, I'm going to show you something else here in a second. But these are elements that enter into that really that development timeline, Don. So right now, Portland cement costs about $85 a ton. And my understanding, again, based on this conversation, is that with no subsidy whatsoever, this alternative right now costs $220 a ton. And clearly that's an issue. Because if you want something to happen quickly, you want it, I know from just based on my experience and my training, you need product advantage, that is property advantage, and you need economic advantage, price or cost advantage. And so this is a Me Too product, and it has a cost disadvantage at the moment, just looking at that number. In spite of that, first of all, the recent Inflation Reduction Act actually creates a subsidy for this type of material of about $30 a ton. Okay, and clearly that's not enough to make it competitive on an economic level with Portland cement. However, I have also mentioned to you that fly ash comes in sort of two flavors. One is buried underwater. It's wet. It could very well be crystalline, and the other version is dried out, relatively new, having been produced more recently from a power plant. And that second version is what is used in cement or Portland cement manufacture nowadays. But both flavors actually can be used by this process. And in the discussion that I had, I got the impression, again, I won't swear to this, but I got the impression that some of this fly ash has to be dealt with by the power companies that have produced it. And actually they are in discussion as to what the price of that might be, or what the power companies might be willing to pay to have these guys take it off their hands. So I know that from what I was told, currently the fly ash price is somewhere in the neighborhood of $85 a ton. And it's likely that that $85 is included in this $220 number that I was given. So I'm just waving my hands here, thinking that I might be able to subtract $115 a ton from this. Okay, so I'm now down to about $105 a ton in cost. So we're now getting close to this $85 a ton. On top of that, there is legislation that's recently been passed in both the states of New Jersey and New York, It was called LECLA, L-E-C-C-L-A, which stands for Low Embedded Carbon Concrete Leadership Act. Again, it's been passed in both New York and New Jersey. And it provides for really a very significant subsidy to any project that uses concrete that net sequesters carbon, which is sort of interesting because this particular alternative does much more than that. And what's interesting about this to me is, again, I work with Citizens Climate Lobby, and I'm going to talk about that a little bit here in just a second. But this legislation, this LECLA, L-E-C-C-L-A legislation on policy, has been implemented at the state level, in contrast to carbon pricing, which actually has to be done at least at the national level. And that implies to me that this type of policy can be implemented at much lower levels of government. And that is much, much easier than implementing policy at the national level, or imagine at the international level. So this policy, in my opinion anyway, just knowing what I know about it, isn't really optimized to incentivize an alternative like this, because this LECLA subsidy is really oriented to providing money. First of all, it provides a subsidy based on the total cost of the project, irrespective of how much concrete is used in it, and how much CO2 is in fact sequestered. So the policy, it seems to me, can be better formulated, perhaps even optimized. But if it's first of all, if it's in place, it lowers the cost of this alternative, or could lower the cost of this alternative, again, significantly, to the point where it then enjoys a price advantage relative to Portland cement. And so that's the that's an element of the economic issue around this, but it's only part of that issue. There's also an issue of how do you go about replacing Portland cement, because I mentioned to you several times now that the confidence that we have in Portland cement and concrete is based on our experience over many, many years, in fact, arguably centuries. And to switch to an alternative is, I will say it's risky, both from a safety standpoint, as well as a financial standpoint. And typically a company that is in the Portland cement business is going to use that to establish an advantage over a competitor. So that would have a tendency, generally speaking, to slow down the implementation or the development and replacement of Portland cement. And it will require, I think, at least an economic advantage to happen. But having said all that, there's a huge potential for this alternative, as you point out, Don, and it's really obvious when you just run the numbers in your head. We're talking about in theory we could replace all the asphalt on roads, for example, and there's an enormous amount of asphalt that makes up roads in just the US. So roughly 18 billion tons of asphalt on US roads that could sequester somewhere in the neighborhood of 3 gigatons of CO2. And then on the top of that, the concrete that is being poured every year would sequester somewhere in the neighborhood of 4 to 5 gigatons of CO2 a year. Okay, so there's an enormous.
Doug, that's absolutely true. And again, very, very impressive. Why should that delay the activity for this purpose? Because how does this affect safety? I mean, to make a delay because of safety means it's stupid.
Well, I mean, I'll just point out one thing. Imagine building a skyscraper using concrete, steel reinforced concrete, and not being really confident that the concrete you're putting in that building will last 30 years, or that will crumble, but that you'll have the situation like you had in Turkey, for example. And the reason we know that in this country that what happened in Turkey won't happen here is because we have regulations in place to require certain types of concrete to be used. And how do we know what we're using? Because we've used this stuff for years and years and years. We have experience with certain recipes that produce properties that we are confident in. And so this new alternative, literally what one of the development stages of this process is to produce many, many different formulas of this alternative, varying the compositions, and then measuring the properties and determining that the properties are equivalent to what we measure with existing concrete and cement. Okay, and then in spite of that, I will tell you that business strategy is such that if I was running the cement business, I would use that against an alternative to maintain viability of my business, right? And so it's just.
I would also point out that their situation in Turkey is that a number of buildings, too many, which were built with the same materials, were built badly.
No question.
No regulation and so on. Now, why is this different? I mean, this is an externality which is not of safety, which is not included in the Portland cement business. I mean, we have to be equal in terms, there has to be equity in terms of the economic evaluation.
No, I absolutely agree with you. I think this has enormous potential, Don. Don't misunderstand me. But I've been trained in these other, I guess, disciplines where I'm anticipating where, you asked how quickly can this be done, I think, to paraphrase you. And these are, when I think about this and I try to think about it objectively, this is where I can see the resistance rising, and it's where I would expect there to be issues. And I know that the people with whom I've discussed this, that they are concerned about the things that I'm just mentioning to you. Okay. So, to try to answer your question objectively, I'm not telling you that I'm not in favor of this. I'm telling you that I think that they will be obstacles or hurdles that this process will need to leap over.
Well, there's statements like we didn't build 50-story buildings 150 years ago. So if we have to change back so that there's a limit while we pursue this information, that's okay. But on the other hand, it's also true that if we were to just reduce the carbon footprint, as you're indicating, by both sequestering and not producing it, in order to do a safe thing like the US roads, why would that delay things? I don't see any economic argument for delaying it.
Oh, well, I will tell you that, you put in, and it's happened, you put in 80 miles of highway and find out that it doesn't meet specifications, starts to crack or something like that, and you have to take it up. That's a huge cost, right? That's very expensive. And so all you have to do to get somebody to slow down making the change is to suggest to them that that's a possibility.
It already exists.
And then you're dealing with risk. Then you're dealing with risk.
It already exists.
What do you mean already exists?
The highways are breaking up now.
Absolutely, absolutely. But now you're saying that this is a different level of it. What you're doing is you're saying that this is riskier. There's more potential variation in this new material because you don't have the experience to fall back on. Okay, you're basing this on all the measurements that you've done, which are, they're not time tested. I'm just telling you that from a business standpoint, if I was running a business, this is the argument that I would make, and I would have to have a way of offsetting that argument by saying, well, I've done all this testing, and not only that, but you're going to save a bunch of money, or something like that, Don.
Doug, this is Tony.
If you need that,
we only have a few more minutes. You might want to move on to the next couple slides that you have.
So, okay.
It's a good discussion, that's for sure.
Yeah. So the last thing that I really wanted to get into, I actually could do something else in addition to this, but here are the benefits. If we implement carbon pricing, okay, if we electrify, if we plant trees, and we substitute alternative cement, this thing that we're talking about right now, I've put this into En-ROADS, and I made a presentation to this group some time ago using En-ROADS, and I actually could do it today as well, where I've tried to model this change in En-ROADS. But I end up with a limit to year 2100 temperature rise to about 1.7 to 1.8 degrees Fahrenheit in En-ROADS. Okay, En-ROADS, which is a simulation model that gives you an idea as to where you're headed. So this by itself won't accomplish the full reduction down to 1.5 degrees. But I will tell you that in playing around with En-ROADS in the past, I've had to do all manner of things in order to get the temperature rise down to to roughly this level. And literally, if I just do these things here, this implement carbon pricing, electrifying everything, which is, what we're in the midst of doing with the Inflation Reduction Act. There's actually a bill out there right now called the Forest Act that's going to plant trees all over the place. If I do those three things along with this, I literally, my estimate, okay, it's perhaps using estimate is giving it too much credit, but it's the best that I can do with a little bit of work, is that we can get the temperature rise down to a level that will be livable. It'll be more than where we are right now, but it'll be livable. And in order to do that, we need local, state, and national policy to develop and implement the changes. Okay? Local, state, and national. The national policy is necessary for the carbon pricing. Electrification is being done both locally and nationally right now with the IRA. The planting of trees can be locally and nationally. It turns out substituting alternative cement can be done locally and nationally. In fact, probably locally more likely. So what can we all do? First of all, we all need to talk to people about the climate issue. Okay, it's always been told to me by people in this arena that the most important thing that any of us can do is to bring this subject up among people that we know, and next to communicate to members of Congress regularly. There's no reason why you can't shoot them an email. Give them a phone call occasionally, tell them that you're concerned about one thing or another. Communicate with state and local elected officials, in particular with respect to these issues where local and state policy can move the needle, okay, especially about electrification, permitting reform that accelerates grid transformation. Permitting reform will also accelerate cement alternative development. Okay, so this legislation and policy that has been implemented in both New York and New Jersey is now being considered in a number of other states around the US at the moment. And it's something that I'm learning more about right now. Ask Congress to institute carbon pricing. Of all the things that I've mentioned today, the thing that actually moves the needle the most is carbon pricing. I will tell you that by far and away, carbon pricing makes the biggest difference. And actually implementing it affects really carbon dioxide emissions around the world. And I always toss in join Citizens Climate Lobby if you haven't already done it. Won't cost you anything. It'll get you in touch with anything that's going on. I don't think that the organization will pester you for money all the time. Although the organization uses some money, it doesn't constantly pester you for it. And it'll make suggestions as to what's on the agenda right now that will make a difference. So that's my pitch. With that, I will, unless you want to look at En-ROADS, I guess I'm done.
Well, Doug, I think I applaud everything you've said. It's fantastic, and it gives you a real feeling for the potential. But the time scale is so extraordinarily important. What is the 1.8 degrees? How is that enabled by the time scale of the shift in those four things?
Well, actually, it is affected very, very much so. I mean, it's a great point, Don. Delaying, as you know, delaying doing any of these things has an enormous impact on where we end up. And it's one of the reasons why, for example, when you look at the simulation, why most of the time nuclear power doesn't save our bacon. And that's because it takes so long nowadays to develop and build a nuclear power plant. It's why oftentimes planting trees doesn't have an enormous effect, because it takes so long to grow a tree. When the longer we wait to do something, the more CO2 goes into the air, ends up in the oceans, and is extremely difficult to remove. Okay, we've got a process here that will accomplish that, but it only does it at a finite rate. And while it sequesters the carbon dioxide that is captured, you've got to put that concrete somewhere. And I don't know that people will want to just build huge concrete blocks, although maybe that's what we'll end up doing.
Doug, this is Tony. I have to agree with Don's comment as far as excellent job as far as pulling this information together. Each time I pull the presentation together, you learn a lot from it. Just trying to pass on the knowledge that you've learned is very beneficial, that's for sure. The one thing I will touch on, and that I'm looking at also as far as alternative, I've got a presentation coming up in a few weeks that's related to planting trees and other things, associated with a homegrown national forest. But I'll also touch on the building that's been constructed in Milwaukee here in the last few years, that all of its columns are made of wood,
right,
laminated wood, and it's 28 stories tall. It's the tallest wood structure in the world at this point in time. I hope there's a lot more development like it. I'll just touch on it. I'm not sure how practical it is yet, although it's been proven, not just here, but in other countries.
right.
This one just happens to be the tallest one. So,
Tony,
the last thing I'll touch on is that carbon sequestration you mentioned, as far as whether you're using fly ash or not. Fly ash is in abundance here in Wisconsin right now because we still have those coal-fired plants.
right.
So I can understand why they have a law to use it up. And if this plant would use it up or do a better job of carbon, sequestration rather than putting it in the ground, put it in the cement, sure seems like a better approach towards the process. So, great job. Thanks much. Sorry about the dog.
Oh, is that what that was?
He's protecting us from the squirrels.
Yeah, I'm sure. You've got. I know you have nuts and berries hidden out in the yard that you're trying to keep away from the squirrels. Well, I think that time is coming to a close here. So if there's nothing else, then I can actually shut this thing off and let
Looks
everybody.
like there's one more comment out there.
Doug,
Oh,
I would just say, I know you probably concerned yourself with the technical details, but that was probably the most comfortable and informative, easy to listen to presentation with that level of technical detail. Good job. That is hard to do. Very hard to do. Good job.
Did it sound like I understood what I was talking about?
Oh, absolutely. Without question. You threw that chemical stuff around like some kind of a mega PhD in chemistry.
Yeah.
But it was very understandable. That's the hard part to do when you're doing a group presentation on a topic that isn't for the U.S. Chemical Society.
Yeah.
Good job. Good job, Doug.
Thanks very much.
All right.
Okay, well.
See you all next week.
Yep. See you guys.